wanted to talk about ARP, Address Resolution Protocol. So where is this used? So let's suppose we have a LAN over here, an Ethernet LAN, and let's say we have node A here and node B, and just let's assume that this has a MAC address BMAC, and suppose it has this IP address, and A has its own MAC address and its own IP address. Okay. And let's say that this is connected to the rest of the internet through some router R. So R itself has its own MAC address and IP address. So suppose A wants to send a packet to B. Okay. And so let's just write that down. A wants to send an IP packet to B. So this is the scenario, and A, let's say, knows B's IP address, which is this BIP. Okay, so let's say that somehow this user, whoever, let's say somebody knows the IP address, and he wants to send a message from A to B. So how is this IP packet going to go to B? So we know that we would have an Ethernet frame, and within this Ethernet frame is the IP packet. And what about the header over here, the Ethernet header? It has to have a source and destination MAC address. So clearly there is an issue over here. How is this frame going to reach B? Of course, inside here is the IP address of B, and of course there would be also be the IP address of A, the source and destination. But we have to send out a MAC layer frame, an Ethernet frame, which has to reach A. And the problem is that A does not know the MAC address of B. So this is an issue. So how are we going to send out a frame like this? Because ideally you want to put B's MAC address here so that it reaches B. So let's think about it. How are we going to do that? So I mean, if somebody says I want to send an IP packet here, the MAC layer is in a fix. It doesn't know whom to send it out. And that's where the address resolution protocol comes in. So the address resolution protocol is going to help us find out the MAC address given that we know the IP address. Okay. So ARP to the rescue. So we can think of the protocol stack as being like this. You have ARP sitting on top of the link layer, and the physical layer. Okay, so initially in the course we talked about 5 layers, but in practice, of course, things are quite more tricky. That's a nice way of looking at things. But in practice, protocols, it's not clear what is above what in some cases. So anyway, for our case, we can look at ARP as being something above the data link layer. Okay, so you can send out an ARP packet which is included, let's say, in an Ethernet frame. Okay, so let's look at what the Ethernet frame would be like. So if you were to send out an Ethernet frame, it would have a preamble, and let's say this is the destination MAC. This is the source MAC. And there is a type or length feed. And then of course inside here you would send out the ARP packet. And of course the frame ends with the CRC. So we are going to send out a frame like this before we send out the packet from A to B, okay, because we don't know the MAC address of B, and this ARP packet is going to help us find it. So how are we going to solve the problem? I mean, we don't know, it's a chicken and egg problem. I would like to contact B to find out its MAC address. But in order to contact B, I sort of need to know its MAC address. So how are we going to do it? And you might have guessed that the solution is some sort of a broadcast. Okay, so we want everybody to be able to receive this packet, this ARP packet, and the appropriate person must reply. Okay, so let's see what this ARP request contains. Okay, so what are we going to send here? So the destination MAC is going to be all ones, and this means broadcast at the MAC layer. Okay, so we already know that all ones in the IP layer corresponds to broadcast. Here we are putting all ones in the destination, so everybody is going to receive this MAC, this particular frame, and they're going to pass it up to the higher layer. Okay, so what does the ARP request contain? So we are talking about this part over here. This would be the ARP request. So it has the sender MAC, and it has the sender IP. So the sender MAC would be what over here? It would be a MAC, and it would have the sender IP, which is its own IP address, and then it has the field called target MAC and target IP. So the target IP it already knows, and the request is going to have all zeros over here. So it sets this field to be all zeros. Okay, so we are talking inside over here. There are these fields inside this ARP packet, and this is what it sends out. Okay, so everybody is going to receive this frame because of the broadcast nature of it. Okay, and everyone is going to look into this ARP packet, and they will look at the target IP, and B will see that the packet is meant for it. Other people will just ignore it because their IP addresses don't match with this. So what does B reply? So there is a ARP reply. So it has the sender MAC field, in which case this is going to be BMAC. So this is the reply. This is from B to A. And this request of course is going from A to everybody, but it's of course meant for B. And the sender IP, which is going to be its own IP address, and of course there's the target MAC and the target IP. So what is it going to put in here? It's going to put a MAC, and this is AIP. Okay. So this is what it sends back, and this is going to be sent out as a unicast. So this is a unicast frame. Okay, so we send out an Ethernet frame which contains of course within this the IP packet, the ARP packet. So there's an ARP, let's say the reply here, and this is unicast, so this is not broadcast. So if we look at the fields over here, we have destination and source. So these are the MACs address, and of course this is going to be A's MAC and this is going to be B MAC. Okay, and all these fields that I mentioned over here go in the reply. So this is how A learns about B's MAC address. It's a relatively intuitive mechanism. You don't have the information you want, so you just broadcast a packet, this ARP packet, ARP request. Everybody receives it and only the concerned person replies with his MAC address. So this is stored, this information is stored in the ARP cache. So the information about B's MAC address stored in the ARP cache at A. So A has to maintain this information. You don't want A to continuously, every time it needs to send out a packet, that it sends an ARP, right? Because that would be an overkill. Suppose it has to send a large file, A is sending a large file to B, and with consisting of millions of packets, let's say, you don't want to send out a million ARPs, right? So you want to cache that information. But there's a slight problem over here in that this may not be a permanent binding. So what if somebody, for example, changes the Ethernet card on his machine? What if B does that? So B's MAC address might change even though the IP is the same, right? Or maybe a network administrator assigns that IP address to somebody else, right? When we talk about DHCP, we'll see how that might even happen automatically, right? So the IP address to MAC binding is not permanent. So this has a timeout. So it could be of the order of minutes, okay, maybe something like 15 minutes, let's say, after which we would get rid of this. And then if A has a packet to send to B, it would again have to send out an ARP request in case the cache doesn't have the MAC address of B. So let's go back to this picture for a moment. And we said that if A has a packet for B, it uses ARP to find the MAC address. So what if B was not part of this network? What if we were sending an IP packet to some C which was not there in this particular LAN? Okay, then sending out an ARP is not going to solve the issue. I mean, what should we do, right? So suppose we wanted to instead send a packet to, let's say this is the internet, the larger internet, and somewhere over here is C, and of course C has its own MAC address, right? So in this case, what are we going to do? I mean, we can't just send out an ARP because nobody is going to reply, right? C is not there on this network, and it doesn't make sense to send out an ARP, right? So what we should instead do is that A should send an IP packet, and who is going to forward it to C? Well, it's this router over here which is connecting this particular local area network to the larger internet. So if A wants to send a packet to C, that particular IP packet should be encapsulated in a frame which is meant for this router. So let's say that A is sending to C, this is an IP packet, and this is the larger frame. So here the destination should be RMAC, right? If in case A is sending a packet to C, because the router's job is to forward this IP packet to the next router and so on, and finally it's supposed to reach C. Okay. So now there is an issue. So first of all, A has to be a little bit intelligent. He needs to know that if at all B belongs to his own local area network or not, right? And if it belongs to his own local area network, he should send out an ARP. If it is not, then what he should do is he should create an Ethernet frame which is destined for R over here, and he should send the IP packet in that particular frame. Now the question is, how does he know the MAC address of R? Okay, this becomes an issue. So let's think about it for a moment. So first of all, how does A know if the destination IP address belongs to his own network or not? Okay, and So if it does belong, then we know what to do, like we did for B, right? And if destination IP is not in the same network, then how does he know the router's MAC address? So if it is not in the same network, so how to know the default router or the default router's MAC address? Okay, so right now we are assuming that there is only a single router connecting the particular LAN to the external internet. So how are we going to do this, right? So first let's talk about one. So A has its own IP address. Let's say a1.a2.a3.a4. Okay. And it also has a subnet mask which is configured in it. Okay, so it, for example, the subnet mask might be 255.255.255.0. Okay, so this is saying that this is all ones. Okay, so how would I know that B's IP address belongs to my own network? Well, if the destination IP and you just take an AND with the mask, okay, is equal to my own address, okay, so this is sort of like the network address. Okay, so this is the mask. Okay, the subnet mask. So all these IP addresses belong to the same network, belong to my IP address, my particular network. If at all the leading bits given this particular mask, if these leading 24 bits correspond to the network address. Okay, so if this is true, then the destination IP belongs to my address. And if not, it does not belong to my network and I would need to send it to the router. Okay, so this is what we would do. For example, with B's IP address, we would first check whether it belongs to my particular network, and if it is, then we said we send out the ARP packet. So now we are interested in the second case, like if we take C's IP address, it doesn't match, and so the packet has to be sent outside. So now the question is, how do I know RIP and RMAC? Okay, this is a issue, and so now actually let's assume that we know RIP. So we'll just discuss this later. So suppose now we know RIP, how do we find RMAC? So you can guess what the answer is, and in that case it is going to be ARP. So it's exactly the same thing, right? So we find that C's IP address is not in our own network, so we have to send a Ethernet frame containing that IP packet for C, and that has to go to the router. Okay, so what we are going to do is we are going to send out an ARP request which is broadcast, which has the IP address of R, okay, as the target IP address, and R is going to reply with his own MAC address in a unicast fashion, in an ARP reply. Okay, so whenever a particular host has the IP address and it does not know the MAC address, it would use ARP, right? Assuming that, of course, that IP address belongs to its own net. Okay, so this is essentially how ARP works. So, of course, we said that we know our IP, but the question is, how would we know our IP? How do you find out what is the default router? So let's go back to this picture. So suppose A is a new machine. Let's say you just bring it up. Let's say everything is blank. Let's say it doesn't have an IP address. Of course, it has a MAC address which is there in the hardware card. Okay, so you can just read what is the hardware address. But it doesn't initially have an IP address. And there is nothing configured, right? It doesn't know the default gateway's IP address. Okay. So what is it going to do? It doesn't know the subnet mask and all those sorts of things, right? It's just sort of blank. It just has a MAC address. Then what are we going to do? Should we sort of manually configure it? And that's one way to do it, where let's say a network administrator comes here. He can't send messages here. That would be very tricky. I mean, how do you send an IP packet here when it doesn't have an IP address, right? So he could manually log into this machine, just physically approach it, manually log in, and he could put in the IP address, the subnet mask, and so on. So that's one way of doing it, but the problem with doing that is that it's prone to error. So suppose somebody makes a mistake and he puts the same IP address for two machines, right? With that sort of human error which can always occur, and that's going to be a problem. Okay, so you want each of these machines to have its own unique IP address. So we would like to automate this whole configuration process, and that is done usually by a protocol called Dhcp. So dynamic host configuration protocol. So this will help a particular host get an IP address, and it will also get information like the subnet mask and also what is the default router's IP address and so on. Dhcp, there's one last thing I wanted to discuss about ARP. So normally what did we say we have in the stack? We have the data link layer, and at the network layer there is IP, right? And here we have typically UDP or TCP, and here you have the applications, right? So we didn't have to worry at all. The data link layer forwards only to a single layer at the next higher layer. Okay, and normally what you have here is the length of the payload in bytes. So you would say how big this particular frame is using these. This actually consists of 2 bytes. So you would say what is the length of the frame over here. But it's also used for type. And why I'm bringing that up is because what if you are sending it up to ARP? So how does the Ethernet layer, how does the data link layer know which is the next protocol layer? There has to be some mechanism for that. And by default it would be IP, but sometimes you may have to send it to ARP, which is another protocol we can say at the link layer. So this is where the type comes in. So if the value is less than so values normally the values are less than 1500, but if the value is greater than 1536, that implies that this field is used for as type rather than a length of the frame. Okay, so if the length is less than 1500, okay, there are some values in between 1500 and 1536 which are sort of not used for some reason, but anyways, if it's greater than 1536, this means that the value here is saying what is the protocol at the next higher layer. And suppose this value is given by 0806, that means that it is an ARP packet. Okay, in this particular payload. Okay, so if you want to send out an ARP request, you would actually put this value over here and send out the ARP packet. Okay? So that somebody receiving it knows that this is not an IP packet, but it's meant to be sent to the ARP module. Okay, so that's a small point. So now let's talk about the DHCP protocol. Okay, so DHCP is used when you want to configure your host. You want to know what is my own IP address, what is going to be the default router's IP address, and so on. Okay, so how are we going to do that? So let's look at this example. So there is a host A, and as usual it knows its own MAC address because it's there in the hardware, but it doesn't have an IP address. And let's say that there is an IP router R. So on this network, let's assume that there is a DHCP server. So the DHCP server should be willing to give out IP addresses to other hosts. Okay, so it should keep track of what are the IP addresses already being used in the network and which ones are available to be given to, let's say, a new host which is asking for an IP address. Okay, so how would we do this? I'll just draw where DHCP sits in the protocol stack. So it sits on top of UDP. Okay, it's something like this. So DHCP is in some sense sitting at the application layer, but of course what it does is that it gives information to the lower layer later on. So for example, A is using this application DHCP to find its own IP address. So DHCP is finally going to populate the IP address over here. Okay, so there is some cross layer interaction over here. Okay. So what are we going to do? So we are going to send out a DHCP packet. We have no idea who the DHCP server is, so of course we'll have to use broadcast. Okay. So we don't know the MAC address or the IP address of the DHCP server. So we would have to do broadcast at IP layer. Okay, because DHCP is sitting on top of IP, so everybody potentially should be able to get this packet. We don't know who is the server. And everybody, of course, first of all has to get the frame. So we are going to do broadcast here too. Okay, so we are going to use all ones in the MAC layer as the destination and also at the IP layer, so that this server is definitely going to get that particular packet. Okay, and how does IP know that that particular packet has to go to DHCP? Well, because the IP packet has a protocol field which says UDP. Okay, and it also has a port number which says that the packet has to go to DHCP. So the port numbers used are 68 and 67. So 68 is used by the DHCP server and this is used by the DHCP client. Okay. So if you have to send out a DHCP packet, this would of course put this as its own port, right? And the port of the destination is going to be 68. Okay, so when we talk later about UDP headers and so on, we'll talk a little bit about these ports. But essentially it's telling you this port number corresponds to the application layer. So it's telling you which application you have to send the packet. Okay, so we are ready. So let's just see what A sends out. So A sends out a frame, let's say a DHCP discover packet. And of course it's going to send out, we are assuming that we are using Ethernet at the data link layer. So this is an Ethernet frame. So we have the various fields here, right? Type field and whatever, and then there is an IP packet sent out. So this IP packet includes the UDP header and so on and the DHCP information. Okay. So this is going to be broadcast, so it's going to be all ones. Okay. And what about inside this? So here the IP packet also should have, I mean, I'm not looking at all the fields, but you have source IP, destination IP, and this has to be all ones corresponding to the broadcast. And of course here this is the DHCP information. So I would say UDP and the DHC application layer information. Okay. So the UDP port number and everything is in here. So everybody is going to receive this frame because they see its broadcast. They hand it up to the next layer, and the IP layer sees that it is a broadcast, so it hands it up to the DHCP application, if at all it is running there, right? Okay, so if port 68 is open, then of course it's going to send it there, but if it is closed, of course it would just discard that particular packet. So the DHCP server is running the server, so it gets this particular packet and it reads this information and sees that somebody wants, let's say, an IP address. Okay, then this particular DHCP discover packet. So what does the DHCP server reply with? So it should send out a packet back to A, okay. And so let's look at the frame. Okay. So this is the MAC layer frame, and this is the IP packet which contains the DHCP information. Okay, let's just say this is the CRC. So A has sent out this discover packet which had broadcast at both the MAC layer and the IP layer. Okay, and the DHCP server received this. So it's going to reply with what is called an offer. And this offer contains a potential IP address for A. Okay, so the DHCP server looks up all its tables, it sees what is a free IP address, and it offers that IP address to A. Okay, so what is going to be over here? So the destination MAC address, of course, is A's MAC address, because this is meant for A. Okay, and the source MAC address is the DHCP server's MAC address. Okay. So let's just say that this has this IP address and this MAC address. So what about the IP packet? So the IP packet also has a source and destination. So the source IP, of course, is going to be from this particular host. What about the destination IP? This is something we have to think about. So one particular IP address is being offered to A, but the thing is that A has not already actually sort of accepted that particular IP. I mean, it's not yet configured. Okay, so you can't really send a packet to that particular IP address and assume that it's going to be received by A. Okay. So what are we going to put here? We are going to put all ones. Which means that we are going to broadcast it. Okay, I mean, at least at the IP layer, I am just putting all ones, because if I put that particular IP address, then A might actually reject that packet because it hasn't already configured that IP address for itself. Okay, so this is how it works, and this contains the offered IP address, and let's just say it's offering this some particular IP address to A. Okay. So the protocol works this way. This is the client, and this is the server. So there's a discover packet, discovery packet, and then there is the offer, and that is followed by a request and an acknowledgement. Okay, so let's say that this offer contained the IP address IP1, let's say, and so what the client is going to say, it's going to contact the server and again say, okay, I'm going to request this IP address, and the server says, okay, you're granted that IP address, okay, and then the server is going to say that this IP address is being used, it will not allocate it to somebody else. So you might say, why do we do it this way? Okay, why do we have two rounds? Why don't you just have discovery and then have the offered IP? So there's more than one reason. So first of all, there could be multiple servers. So there could be, let's say this is the server 1, and there could be a server 2. Okay, and this discovery is broadcast to everybody. So maybe a offer comes from this server 2, and let's say there is a second IP address offer. Okay, so now you clearly see multiple offers have been made, so it doesn't make sense for each of these servers to say that both IP addresses are being used now, right? Because only one of them is going to be accepted. So the client in this case, let's say, prefers IP1 for whatever reason, it chooses among these, and it sends a request and an ACK. Okay, and this server says that IP1 is needed. So this server didn't get a request from the client again, so IP2 is still available to be allocated to somebody else. So there is also a second reason. So before actually accepting an IP address, the client does a double check. Okay, so it checks if this particular IP address is used by anyone else. And how would it do that? So if you have an IP address and you want to know that somebody is using it, what you could do is you could send out an ARP packet and see if somebody replies. Right? If somebody replies with his MAC address saying that I am using IP1, then you know that it's already being used, in which case you would not send this request. So this is like a double check in case the server there's some problem, it has sent you an IP address which is being used by somebody else. Right? Okay, so for these two reasons we have this sort of two-way hand, or I would say four-way handshake, where you send one message, you get a reply, you send another request, and you get an acknowledgement. Okay, so this is how DHCP works, and you can learn your own IP address, and you can also, of course, inquire about other information from the DHCP server, like the default router's IP address also. Okay, so the DHCP server could send you the default router's IP address, and if you want the MAC address, then of course you could use ARP. Okay. So it's possible that in case there are, let's say, multiple LANs, you might even have a common DHCP server for multiple networks. So let's say there are several of these. let's say we have something like this, and let's say that there's a common DHCP server for both. Okay. Now, how are we going to find out an IP address? So A has its own MAC address, but it doesn't have its IP address. So it's going to do a broadcast over here, a local broadcast. Okay. Now, if you have the destination IP address as all ones, you might wonder, why doesn't this packet actually go to the whole internet? I mean, after all, it's a broadcast, right? So why doesn't it reach everybody else? So the reason is that this gateway router will not forward IP broadcasts beyond the own network. Okay, and that's thankfully, because you don't want to get every broadcast sent by everybody in the world. I mean, that would just flood the whole internet. It doesn't make sense. So whenever you put all ones, it will only go to your local network. It will not go beyond that. Okay. So we send out a broadcast at the MAC layer and at the also at the IP layer. Okay. So this is at the IP layer. This is layer 3. So it's not going to forward IP broadcast beyond it. And the DHCP server is not in this particular subnetwork, right? It's somewhere else. And of course, we may want to do this because maybe this is a small network. You don't want to have a dedicated server if there are, let's say, 5 machines here. I mean, it's an overkill. Maybe you have lots of subnetworks and you just want to have one DHCP server. So how is DHCP going to work over here? You send a broadcast and it's not going to reach the server. So intuitively you might think what may be the solution. So you have a relay agent. So the relay agent is not going to do the dirty work of keeping the full table of IP addresses used and so on. Right? It's just going to act as a sort of a proxy for this particular DHCP server. So when A sends out the DHCP discover, so it sends a discovery message, and this is broadcast. The relay agent is going to receive it, and it's going to unicast a packet to the DHCP server because it knows the IP address of the DHCP server. And the DHCP server is going to reply back with an offer, and this is unicast to the relay agent. And the relay agent is going to forward that message. It's going to send it. Okay, it sends out the offer, which will be received by A. Okay. So this is how it works. This sort of acts as a proxy between the two of them, and the protocol will proceed as it is. Okay. So this is just how you would get a network up and running, and you would get a host if you plug it in. Normally you would want to use DHCP to make things simple, right? And you get your IP address and the default gateway IP address and so on, right? So this is how you would normally set things up. And subsequent to these particular topics, we look at BGP, which really puts the entire internet together. It's sort of like the glue logic connecting all the different networks together.